So in the previous video, I showed you how we can derive Gauss's law from one of Maxwell's laws using divergence as a concept. So now I want to show you how Gauss's law can be useful to get some more general results than you can get otherwise. So first things first, we're going to look at a spherically symmetric charge distribution. So this little dot just means any way you rotate it, it's going to stay exactly the same. So the field has to be exactly the same no way you rotate it. So the field can only be dependent on your distance from it. Because if, say, at this point, that's distance r away, the field is something, and then it's something completely different at this point, then if you rotate this, then that wouldn't still be the same, but your charge distribution would be the same, which would be a contradiction. So, due to our symmetry, we can therefore say that the intensity of the field at the very least is only dependent on the radius from it, and it always has to be radially outward, since it's a spherically symmetric charge. There's no way it can produce a field that goes around or whatever, so you're always going to have either radially inward or radially outward. So therefore we can write this, which is a vector of the electric field at any point, which is just our position vector, can be rewritten as some scalar function that's only dependent on the magnitude of your position. So that's only how far you are from the center of this charge, and it's always going to be in the direction of the radius vector. So remember, E of r can be positive or negative. If it's positive, it's going to be outwards. If E of r is negative, it's going to be inwards. So then we can make a couple of observations. We start with Gauss's law. So we have the surface integral over a surface of the electric flux at that point, which we're going to just denote as this, the electric field dot the dA. So that's just the electric flux at that point. Just normal law is going to be your total charge that's enclosed in that surface divided by epsilon naught, also called the vacuum permittivity. So now we can start to notice some things that will simplify this. First of all, we already simplified it to this scalar equation. Next, we're going to have a much simpler time if we use a sphere around this charge distribution, because if we use a sphere, that means that every point on that sphere, every point on the surface, your magnitude is going to be a constant. So this stays constant throughout this integral, which makes the integral a lot easier. We can just pull this out as a constant factor, and since we know that we have a sphere, the normal vector is always outwards from that sphere. It's always going to be in the direction of the radial vector. So the direction of this area to relatively to this, they're exactly parallel. So their dot product is just 1. So we effectively only have the integral over the entire surface of the sphere times our electric force's magnitude at one point. So how much it is at this point times the magnitude times the surface area of the sphere will give us the total flux in that area. And we know the total surface area of a sphere is just 4 pi r squared, and then we still have this constant here, that is our function E of r, which is constant at a certain radius, which made our previous integral easier. Now we can just do some algebraic manipulation here, and we get something for the magnitude of the field at a certain radius. This starts to look very familiar. Then we notice that if we take this scalar part and multiply our unit radial vector with it, we get the actual field at this point, the vector field. So if we multiply the radial vector on both sides, we get the field. So you can see that that's a vector field. There's a little arrow above that. I'm not sure if you can see that. I see the quality is not perfect. And then you get this, which is our usual expression that we already have for a point particle. So we can see that any spherically symmetric charge distribution will behave identically to a point particle, which is very convenient. We can do something else, and we can multiply q on both sides, since we know that the definition of the force on a particle that has charge q is the product of that charge with the electric field at that point. That's just the definition of the electric field. It's force per charge. So if we just multiply the q on this side, we get this. Now the interesting thing is, if you just take this 1 over 4 pi epsilon naught and we call that k, you're going to get exactly the Coulomb's law that we did in high school. And so from just using some symmetry and Gauss's law, we can already get the Coulomb force, and we get the expression that's not only valid for a point particle, but also valid for any spherically symmetric charge distribution. And that is the power that we have with Gauss's law. So the next part that's quite important in many cases with Gauss's law is the concept of field lines. So the definition of a field line is merely it's a line that's always tangent to the field at that point. So if we had the field at this point and its vector is pointing at in this direction, it needs to be tangent to this line. So if you look at the electric field at any point on this line and look at that vector, it's always going to be tangent to this line. That is just the definition of electric field lines. So technically around any charge or anywhere in any field, you can draw infinitely many field lines, but that's not very helpful. But what you can do is if you draw a certain amount, one of the nice features of these lines, due to Gauss's law, is how the closer that these field lines are to each other, the stronger your electric field is at that point. So if we look here near the charge, we can see that there are a lot of field lines in this small area, so we know it's going to be a very strong field. While far out, we can see in a certain area, there are much less field lines that you can see in that area. There's only, let's say, 1, 2, 3 here, but in the same area here you can see 5. So, because there are less field lines, we know that the field isn't as strong there. So, using this, Gauss's law becomes quite intuitive, because obviously field lines have to continue. They either start or end on a charge, or they go off to infinity like this one. It just goes on forever. So the field line can't just disappear. These all technically continue. I just can't draw infinite lines, sorry. So if we use that intuition, we can think about a surface, and then if we think about the lines going through that surface, the same amount of lines that come in have to come out if there isn't a source or a sink for field lines inside there. If there is a charge, it will create new lines inside of it, and therefore your flux your net flux won't be the same. But if the charge is outside, the field line has to go in, but also out. And if it goes in, it gets exactly cancelled out at the point it also goes out. So then obviously the electric flux has to be related to the charge enclosed by that surface. So that gives another perspective on what Gauss's law actually tells us. So now I want to use Gauss's law to talk about conductors and how the charge on a conductor is always going to go sit right on its surface. So one of the observations that's going to be very important to us is that the electric field inside a conductor must always be zero. Why is this? Well, if we imagine that there is an electric field inside this conductor, it's either going to be a straight line that's eventually going to hit the side, or it's going to go in a loop. But if it's in a loop, that's going to mean something like electrons just going to keep on going there, and that's basically infinite energy. And we know that there's conservation of energy, and this thing's just not going to keep on heating up because of resistance or whatever. So we know that's impossible. That's not going to be inside of a conductor. So therefore, if there are electric field lines in here, they're always going to point eventually outside. So your charge is always going to be pushed to the edge. It's always going to end up here. And it doesn't take very long, because most conductors aren't very big compared to how long that takes. So if you have a charge in you and you have some time, then it's always going to go sit right on the edge. So this gives us something else to observe. Since our electric field is zero here, we can also, instead of just reasoning, we can use Gauss's law. Since if we draw a surface inside here, we can maybe draw it just here to help with visualization. So if I draw a random surface inside that doesn't intersect with the outside, so we know everywhere here the electric field is going to be zero. And since the electric field everywhere on this surface is going to be zero, that means the total flux through this surface must also be zero. And if the electric flux through the surface is zero, then we know the charge enclosed in the surface must also be zero. And if the charge enclosed in any surface that's drawn inside the conductor is zero, that means that there's no charge on the inside, but everything sits on its surface. So we can use Gauss's law quite easily to go from just the fact that the electric field is zero everywhere inside a conductor to the fact that the charge will always distribute itself on the edge of this conductor. So that's one of the ways that we can use Gauss's law.